Welcome to this Mathcast. In this episode, we're going to be looking at sort of the foundations of conditional probability, the formulas involved, and essentially the idea behind it. To talk about the idea behind it, I want to look at essentially the question that we're trying to answer in this Mathcast, and that is, does having knowledge of the occurrence of previous events, in other words, knowing what happened before, does that affect the probability of an event? So it's a very open-ended question. What we're basically asking is, does knowing that something's occurred beforehand affect the probability of it happening now? And to demonstrate this, I want to look at an example. We're going to go back to our card sample space, and this time I'm going to suppose that you draw 2 cards. Once again, these are cards from a 52 card deck. And I want to sort of compare and contrast 2 different events. So I'll call one event 1. And event number 1 is that I draw a heart and a club. Event 2 is that I draw 2 clubs. Alright, let's break down event 1 first. If I was to look at heart and then a club, the probability of a heart is easily 13 out of 52. The probability of a club is normally would be 13 out of 52, but because this is occurring after I've already chosen a heart, meaning I'm doing this without replacement, so I'm drawing the cards and I'm not replacing them, then there is 1 less card overall to pick from, so it's 13 out of 51. So I want to make sure that you understand where that's coming from. This is, there's 1 less card to choose from overall. So if I'm trying to find the probability of event 1, the probability of heart and club, we know that the word "and" means to multiply here. So I'm multiplying these 2 together. And we're not really concerned with what the actual number is here just yet, but this is what probability of event 1 would look like. Compare this with if I was trying to do the same thing now for event 2. Well, event 2 is 2 clubs, so I've got the probability of a club first would be 13 out of 52. But then if I tried to draw a club again, so I'll just say club on second try. Well, since I've already drawn a club previously, there's only 12 of them left in the deck. And that lessens 1 card total, so it's 12 out of 51. In this case, the probability of this event would be the probability of a club times the probability of another club. But it's this second club that we're drawing that is the focal point of this Mathcast. And the reason for it is, if you look, in both problems I was asked to find the probability of a club coming up second. However, depending So sorry, this should be 12 out of 51. depending on what was drawn previously, it changed. The probability changed. So the probability of drawing a club second changes. Well, this is sort of a problem for us. We can't just say the probability of a club and know which of these two probabilities we're talking about. And realistically, that probability is not even dependent upon me asking you to draw a club. It's dependent upon me asking you what happened before you drew the club. And that's why this is called conditional probability. The probability is conditional on what happened before. So we need some notation to handle this. Normally, when we talk about multiplication rule, the probability of A and B is the probability of A times the probability of B. We've dealt with multiplication rule at several different steps along the way here, both in counting and now in probability. But as you can see, this is not enough. We really need a better formula, if you will. And if we're going to change the formula, we need to somehow change this probability of B to represent the fact that it's following the event A. And this is how we do it. We define the conditional probability of B as follows. It's the probability of B given A. Now I want to make sure we understand sort of what's going on here. This vertical bar means given, or given that, depending on the circumstances, but given the probability of B given that A has occurred. And the formula for this is the probability of A and B occurring simultaneously divided by the probability of A occurring, and this is only if the probability of A is non-zero, because we can't have a zero in the denominator. Alright, well, let's apply this to this event 2. So I want to look at the probability now of getting 2 clubs using this formula. This is the probability of getting a club first times the probability of getting another club, but given that I've selected a club already. So this first probability is very easy. The probability of selecting a club first we know is 13 out of 52. And now I have to figure out the probability of this conditional probability, which we know is 12 out of 51. But I want to show you, in other words, we know this number is going to be 12 out of 51. But I want to show you where that number comes from. And it comes from using this formula right here. This is what I'm going to be using to figure that out. So I need the probability of A and B. The probability of A and B is the probability of these 2 clubs. Well, the probability of A and B being 2 clubs means I have to pick out of a deck containing 52 cards, I have to pick 2 clubs. And it doesn't matter which order I pick them in. So this is a combination problem, and what you get is you get a 1 out of 17 chance of that occurring. Alright, I then need to divide by the probability of A, and the probability of A we know is the probability of the first thing happening, which is the club, is 13 out of 52. So the conditional probability says that I need to divide these two. If you take 1/17 and divide by 13/52, remember you have to flip the denominator here, what you'll get is 1/17 times 52nd 13ths, which turns out to be 4/17. And so the only question we have left is 4/17 the same thing as 12/51? And the answer is yes, this is also 4/17. So it's sort of unusual here. I mean, we were able to easily come up with the probability just by sort of thinking through it, but sometimes just thinking through it's not enough, and you need to know how to calculate these conditional probabilities. And the answer is this formula right here. This is the formula you need to know to calculate conditional probabilities. So I hope this has given you a little bit of insight into how to calculate these conditional probabilities, when they show up, why we need this extra notation, this vertical bar that means given that, and some of the underlying principles behind what we're doing here. Thank you for watching.